We continue looking at Gauss's law. The figure shows an insulating sphere of radius r. Capital R, that's the radius of this sphere. And we have positive charge embedded evenly throughout. We can see here from the picture that rho is a constant. Now, what's rho? Rho is called the volume charge density. And the units are charge per volume. So that's going to be coulombs per cubic meter. Previously, we've met lambda, which is linear charge density, and that had the unit coulombs per meter. Well, rho is volume charge density, coulombs per cubic meter. Now what we want to do is we want to derive an equation for the electric field as a function of little r. First, when little r is less than big R, and then when little r is bigger than big R. So let's draw a Gaussian surface, a Gaussian sphere, isn't it? First, when little r is tinier than big R, kind of like that. So that's a sphere there. That's not a circle, it's a sphere. Gauss's law says that the charge that's enclosed over epsilon naught is equal to the integral of E dot dA. Now, what's the charge that's enclosed in here? Well, the charge that's enclosed is just the charge that's inside this Gaussian surface. The charge that's on the outside, totally irrelevant to using Gauss's law. So what is that charge that's inside? Look at the unit for rho. It's coulombs per cubic meter. So if you want coulombs, you're going to have to take rho and multiply by volume. Now, what's the volume of this little guy? The volume of a sphere, isn't it 4/3 pi little r cubed? So that's Q enclosed. Rho times 4/3 pi little r cubed. The electric field at each point on this Gaussian surface is equal, so we can pull that E out of the integral. That leaves us to integrate this dA. And when you integrate dA, you just get A. And so what's the surface area of this little Gaussian sphere? It's 4 pi little r squared. There we go. We've integrated dA to give us A, and A is 4 pi r squared. We can cancel some things. The 4 and the pi will cancel. These two r's will cancel two of those. And I think if we simplify that, we can find the expression for the electric field at any distance r. It looks to me like it's going to be rho times r over 3 epsilon naught. So according to this equation, as we go further out from the center here, the electric field is getting stronger. As r gets bigger, the electric field is going to get stronger. What about when little r is bigger than big R? There's big R. It only goes to there. Now our variable is going to go out here. So that's where our Gaussian sphere needs to be drawn. There we go. Let's use Gauss's law again. Q enclosed over epsilon naught is equal to the surface integral of E dot dA. Now, what's the charge that's enclosed here? Well, the charge that's enclosed only extends out to big R. So we're going to take the charge per unit volume, rho, and we're going to multiply by the volume that has that charge in it, which is 4 pi big R cubed. You see, not little r cubed. Little r came into play in the top diagram because little r went all the way out to where the charge is. But in the bottom diagram, the charge only goes out to big R. So we have to stop there. Now, on the right side, E is a constant, so we can pull that out. We can integrate dA, and when you integrate dA, you get A. So what's the area of this Gaussian sphere, it's 4 pi little r squared. So we can cancel some things again, but not as much. 4 cancels, pi cancels, but I think that looks like it's it. E is going to equal what? I'm seeing rho big R cubed over 3 epsilon naught and then little r squared in the denominator like that. All right, the next part there says, this is at the bottom of your screen, show that when little r equals big R, the part B answers yield the same result. So right at the surface, if we did this correctly, these two should give us the same answer at the surface. And you can see what's going to happen. If I put big R into this top equation, we get, and I'll just write it right here, rho times big R over 3 epsilon naught. I put big R right here, the top of the screen. If I put big R right there. If I put big R down here in the denominator, you can see I've got big R squared, but in the numerator, I've got 3 of those big R's. And so do you see this? I think we're onto something. We get the same answer at a value of big R for both of our cases, where they should agree, because that's where they meet up. All right, let's finish by making a graph of E for the insulating sphere. Let's look at the top equation. E is going to increase linearly with little r. So the first part of the graph is going to look like that, and it's going to increase linearly all the way up to little r equals big R right there. E is proportional to r in that section. Then, what does the equation tell us? Can you see this? There we go in the upper left. As little r continues, now the electric field is proportional to something over r squared. What does a something over r squared graph look like? Doesn't it look kind of like that? Here, based on our equation, the electric field is proportional to 1 over r squared.